This is SpaceTime Series 20, Episode 60. Coming up on SpaceTime, planet Earth about to have an extreme close encounter with a potentially deadly asteroid. The mystery of the cosmic cold spot deepens. And new evidence that the Higgs Boson decays into quarks. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
On October the 12th, an asteroid known as 2012 TC4 is likely to fly just 6,800 kilometres above the surface of the Earth, far lower than the orbits of many satellites. The 40-metre wide asteroid won't be hitting the Earth this time round, but it will be about as close as possible while still passing safely. By comparison, the meteor which airburst in the skies above the Russian city of Chelyabinsk in February 2013, injuring some 1,500 people and damaging over 7,000 buildings, was just half that size. 2012 TC4 was discovered by the Pan-STARRS 1 telescope on Maui in Hawaii in October 2012. A week later it flew past the Earth at a distance of 94,800 kilometres. TC4 is an elongated, rapidly rotating object on a 1.67 Earth-year orbit around the Sun. The mere fact that this asteroid will come so close flags it as a potential future Earth impactor. Based on science's current understanding of its orbit, and that's based on just 7 days of observations between October the 4th and October the 11th, 2012, TC4 only has a 0.00055% chance of hitting the Earth. Astronomers now know that this house-sized space rock's already made several close approaches to Earth in the past and will undoubtedly do so again in the near future. Of course, the important message from all of this is the fact that the Earth will be hit by a large asteroid sometime in the future. We know 2012 TC4 is safe until at least October 2020. But the thing is, there are lots of other asteroids out there which we know about which could pose a serious threat to this planet, such as 99942 Apophis. The half-kilometre-wide asteroid Apophis first raised concerns back in December 2004. Initial observations back then indicated a probability of up to 2.7% that it would impact the Earth on April 13, 2029. Additional observations providing improved predictions later eliminated the possibility of an Earth collision during that close encounter. However, until 2006, the possibility remained that during the 2029 close encounter with Earth, Apophis would pass through a sort of gravitational keyhole, a small region no more than about 965 kilometres wide, which could set up this mountain-sized space rock for a future impact exactly 7 years later on April 13, 2036. This possibility kept Apophis at level 1 on the Torino Impact Hazard Scale until August 2006, when the probability that Apophis would pass through the keyhole was determined to be extremely small. And by 2008, the keyhole, which was originally thought to be about 1,000 kilometres wide, was determined to be less than 1 kilometre wide. However, during the short time it was of greatest concern, Apophis set the record for the highest rating on the Torino scale, reaching a level 4. The Torino scale is a method for categorising the impact hazard associated with near-Earth objects, or NEOs, such as asteroids and comets. It's intended as a communications tool for astronomers and the general public to assess the seriousness of collision predictions by combining probability statistics and known kinetic damage potentials into a single threat value. And while potentially deadly asteroids like Apophis are well studied and known, there are lots of other asteroids out there which are yet to be discovered. And for scientists, that's where the real threat lies. Meanwhile, NASA says it'll use the TC4 close encounter as a test of the agency's new planetary defense network. NASA's conducted such preparedness drills rehearsing various aspects of asteroid impact, such as deflection, evacuation and disaster relief, with other entities in the past. Traditionally, however, these exercises have involved hypothetical impactors, and that's prompted Professor Vishnu Reddy from the University of Arizona to propose a slightly more realistic scenario, one that involves an actual close approach of a near-Earth object, or NEO. The observational campaign will allow scientists to exercise the network, testing how prepared the Earth really is for a potential impact by a hazardous asteroid. NASA's Planetary Defense Coordination Office, America's federal entity in charge of coordinating efforts to protect the Earth from hazardous asteroids, accepted Reddy's idea to conduct the observational campaign as part of assessing its own Earth-based defense network. The agency identified the upcoming approach of 2012 TC4 as a great opportunity to conduct the exercise. The goal of the TC4 exercise is to recover, track and characterise the asteroid as a potential impactor in order to exercise the entire system from observations, modelling, predictions and communication. The exercise will involve more than a dozen observatories, universities and labs across the globe, in the process collectively learning the strengths and limitations of Earth's planetary defence capabilities. Since its discovery back in 2012, the uncertainty of the asteroid's orbit slowly increased, as it would for any asteroid as time passes. Therefore, the first order of business will be to recover the object. In other words, nail down this asteroid's exact path. Depending on its predicted brightness, or albedo, the asteroid should be visible again in large ground-based telescopes later this month. Planetary scientist Dr. Simon O'Toole is with the Australian Astronomical Observatory.
We know a very approximate size, sort of somewhere between 20 and 40 metres. We know when it will fly by the Earth, and we know that it will not impact the Earth. We don't know exactly how close it will go. It will be no closer than 6,800 kilometres, but it could be as far away as 270,000 kilometres.
That's around halfway to the moon, isn't it?
Yeah, that's right. That's right. So part of this project is to actually really pin down quite exactly how far away it is, what its size is, and all of these things as part of a planetary defence coordination office. So basically, it's a project there, and it's a good target because the actual size and the actual distance or approach, closest approach, are not known. So it's sort of something where they can track these with a whole bunch of telescopes around the place and try and pin down these numbers a bit better. It's sort of the asteroid is around the size of the Chelyabinsk asteroid of February 2013. It's a good project. NASA and a bunch of scientists from the Lunar and Planetary Lab at the University of Arizona are leading the campaign. So it's a good chance to really test out their planetary defence system.
How would you like to be one of the dudes or dudettes who actually have that in their title? What do you do for a living? I work for planetary defence. That's pretty
It sounds awesome. It's so cool.
Now, this is a what if. If it's an asteroid, say, 40 metres across, an iron asteroid, what sort of damage could that do if it were to hit the Earth?
If it were to hit the Earth, you'd definitely get a pretty substantial crater. Certainly, if it was a solid iron block, it would cause substantial damage. There would be an impact site, so a crater. You'd have the sonic boom, so you'd have basically all the windows and things shattered. Lots of quite serious damage to buildings in the vicinity. Yeah, and a shockwave that would, as I said, break glass and everything. So similar in some sense to the Chelyabinsk incident where, a whole bunch of people were injured and 7,000 buildings had their windows broken, but there would actually be damage to buildings or any structures as well. Whereas Chelyabinsk, I don't know if very much of it came down and impacted the ground.
With Chelyabinsk, it's hard to tell what was real and what was make-believe or woo, simply because there were so many opportunists to say, hey, I've got a piece of the meteorite for sale here.
Exactly.
I think a small chunk landed in the lake nearby, but that's about it.
Yeah, that's right. That's right. And certainly if you had the other sort of extreme, the 40 metre size was the largest size, and iron is the densest
that's why I went with
likely constituents. Yeah, but by the same token, if you went with the other end, sort of 10 metres across and sort of an icy rocky thing, then it'd probably burn up entirely in the atmosphere. You'd still get the shockwave and the broken glass, etc., and probably some minor damage, but I wouldn't expect anything more than that. Whereas, yeah, certainly a 40-metre iron block would cause substantial damage, probably tremors and things like that on impact.
Of course, it wasn't all that long ago that we celebrated the anniversary of the Tunguska asteroid impact as well.
Yeah, exactly. Although that was more of a... Was that actually an impact, or was it more of an airburst?
Again, that was an airburst, and they're pretty sure where it airburst because of the butterfly pattern of the tree devastation that was caused in that forest where it exploded over. The trees directly under the point where the asteroid exploded in midair, they remained standing because the shockwave was going straight down. But everything around it was flattened in whatever direction the shockwave was moving away from ground zero.
Yeah, exactly. So, that to me at least suggests that it was, not solid iron, but it was pretty large. I think it was bigger than the Chelyabinsk one.
Yeah, I think they estimated that one at about... Chelyabinsk, there are still varying estimates between 15 and 20 metres. Tunguska, I think, is in that 20 to 40 metre range already, but probably not iron. Yeah. With a close flyby we had on the same day as the Chelyabinsk incident, we of course had an asteroid pass below the level of satellites off the Indian Ocean coast of Western Australia. I take it we can't be that precise as yet with this one?
No, and that's part of the exercise that they're undertaking, is to really pin down the orbit. So basically they'll have a much better idea as we come close to the 12th of October where the closest point will be, but at the moment it's because we can't even say if it's going to be 7,000 kilometres or 270,000 kilometres. I mean, that's a very large range, which also means that on the Earth it's quite a large variation as well. So really, I think that's not pinned down, and that's part of this project, is to track it as best as possible. So we can't say where, but probably October 9, October 10, we'll have a pretty good idea of where it will go.
So just shortly beforehand, we'll have a rough idea of exactly how close this encounter will be. How do we find out what it's made out of? We only have its albedo at this stage.
You use lots of different kinds of telescopes. So you look at not just its visual light, but you look at infrared, you look at microwaves, radar, they'll use radar, all sorts of things like that. And then you look at the reflectivity of it, and you try and sort of do some kind of spectroscopy to determine what kind of body would reflect in the way that it does across all of these different wavelengths.
The fact that its last close encounter wasn't all that long ago, 2012, I guess that tells us that this thing's mainly hanging around the inner solar system all the time.
Yeah, that's right. It's certainly one of these near-Earth objects. So it's in or around the orbit of the Earth, and we catch up to it as well. So it's moving around, we're moving around. So, I mean, I think from memory, there's nothing, I mean, this is relatively small. There's nothing very large at all that's with any chance of impact. This is the closest, and it's pretty close. So it is a good opportunity for this planetary defense team to track it and to really try and understand not just the object itself, but how to track these kinds of objects in this kind of way, like in this very precise, very targeted sort of way. Because most of the time, amateur astronomers discover it, or the various survey telescopes discover it, but then amateurs follow it up for a little while, and then it gets forgotten about, and then they find it again, and there's not very much really targeted follow-up in the same way that this system will be.
The more observations you can get, the better you can pin down what its orbit is.
Yeah, exactly. So you've got to be from different places on Earth, so you've got to factor in where you are and your latitude, longitude, and your altitude, and all of these things in order to really get an accurate trajectory, orbital path. But the more you have over several days, the better your chances of knowing exactly where it will be at any one time in the future is.
When asteroid 2012 TC4 passes close to the Earth in October, that will undoubtedly deflect and change its orbital trajectory, won't it?
Yeah, I mean, certainly the gravitational sort of significance of Earth, it will have an impact on its trajectory for sure. It can't not. And it probably already is. We're still months away, but it's having an impact even now because it would be the closest body to it. So yeah, I mean, any planet in the solar system, in Jupiter still has an impact. It's very small, and it's not as much as the Earth as it gets closer, but it's being so massive, Jupiter and the Sun still dominate the gravitational pull, except for objects very close by.
As a planetary scientist, is this the sort of thing that gets you excited?
In some ways it's hard not to be blasé, because it's just like, oh, well, it's not going to hit it, so we're fine. But certainly it's pretty cool. I mean, to me, I actually look at these sorts of objects as, this is the building blocks of the solar system. So that's where I'm probably more interested in how planets and planetary systems form. So from this point of view, I'm interested in these objects, not so much as what are they going to collide with Earth. I mean, obviously I'm very excited that it's not, but more that what's it made of. That's my interest in this sort of work, is what is this thing made of? Where did it come from? What does this tell us about the origins of our own solar system? I guess that's my primary interest, and the other is, of course, humanity's survival.
I'm just looking at some of the headlines associated with this. Will asteroid 2012 TC4 hit the Earth in October 2017? That sort of thing, does that worry you at all? Or you think people understand this is just done as clickbait?
I do get concerned because a lot of people can get very panicky about this sort of thing. I think that it's not helpful, and part of my, I'm very aware. I think NASA does a really great job here, but there are plenty of people out there who use this as an opportunity to promote themselves by creating panic, and they become the person to listen to. So I am very wary of that sort of clickbait type sensationalism, because it's not really necessary to ask that question, because obviously
the answer is no.
We know the answer. The answer is no. Exactly. So my concern is that by asking that question, people don't even read much beyond that headline, and they go, Have you heard about that asteroid that's going to run into us? But that's as far as they go. They don't go any further. So, that's probably my concern.
And then when it doesn't happen, people say, oh, the scientists got it wrong again, when actually the scientists haven't got it wrong. It's the idiot who wrote the story that deliberately twisted it.
Yeah, that's exactly right. And that's not very helpful for anyone. So I do get very frustrated with those sorts of headlines. And then because it also encourages it just feeds into the whole Nibiru brown dwarf entering our solar system to destroy us all, conspiracy theory stuff. I don't know if you get emails about that, but I do.
I'm shocked to find the flat Earth people are still around. I couldn't believe. I thought they were gone 2,000 years ago, but no, they're still here.
Apparently not.
That's Dr. Simon O'Toole, a planetary scientist with the Australian Astronomical Observatory. And as we get more updates on the close approach of TC4, we'll keep you informed. You're listening to Space Time. I'm Stuart Gary. Astronomers are still at a loss to explain a gigantic cosmic cold spot in their large-scale maps of the universe. The mystery deepened after reports in the monthly notices of the Royal Astronomical Society ruled out the most likely suspect, a gigantic supervoid, a huge empty region of space containing fewer than the average number of galaxies in a given area. And that's leaving the door open for more exotic explanations, such as a possible collision between universes. The large-scale structure of the universe looks a bit like a giant web, with filaments and nodes full of galaxies and galaxy clusters surrounding vast empty voids. The cosmic cold spot was first discovered in images of the cosmic microwave background radiation, a sort of snapshot of the early universe, taken when the cosmos was just 370,000 years old. That's the time when the universe cooled down enough to allow the first atoms to form and photons to escape. Today, the cosmic microwave background radiation has cooled to just 2.73 degrees above absolute zero, minus 270.43 degrees Celsius. But the cooling isn't uniform. There are slight temperature variations in the cosmic microwave background radiation, representing areas of greater or lesser density, regions which would eventually evolve into the galaxies and galaxy clusters we see today. Generally speaking, these temperature variations are spread out fairly evenly across the cosmos. Except that is for one region, which scientists are now calling the cold spot. The cold spot's about 0.00015 degrees colder than its surroundings. Scientists originally thought the cold spot would be explained by a supervoid billions of light years across, which contains relatively few galaxies. However, new research by Rory Mackenzie and Professor Tom Shanks from Durham University has failed to find any evidence of a supervoid at the location of the cold spot. Their study was based on the accelerating expansion of the universe, which causes voids to leave subtle redshifts on light as it passes through them. In the case of the cosmic microwave background radiation, this is observed as cold imprints. It had been proposed that a large foreground void could, at least in part, imprint the cold spot into the cosmic microwave background radiation. But that hypothesis has never been universally supported, partly because it raises issues with science's current models of standard cosmology. Previously, most searchers for a supervoid connected with the cold spot have estimated distances to galaxies using their colours. You see, with the expansion of the universe, the more distant galaxies have their light shifted to longer and longer wavelengths, an effect known as cosmological redshift. Put simply, the more distant the galaxy, the higher its observed redshift. By measuring the colours of galaxies, that is their redshifts, their distances can be estimated. The problem, though, is that the measurements have a high degree of uncertainty because of other factors. So in their work, Mackenzie and Shanks presented the results of a comprehensive survey of the redshifts of some 7,000 galaxies using a spectrograph on the Anglo-Australian telescope. And it was from this higher fidelity dataset that the authors failed to find any evidence of a supervoid capable of explaining the cold spot within the standard model. Researchers instead found that this cold spot region, which before now was thought to be underpopulated with galaxies, is in fact split into smaller voids surrounded by clusters of galaxies. And that gives it a soap bubble structure much like the rest of the cosmic web. Mackenzie says, put simply, the voids which have been detected cannot explain the cold spot under standard cosmology. And that raises the possibility that some non-standard model could be proposed to link the two in the future. However, Mackenzie and Shanks' dataset places strong constraints on any attempt to do that. Now, if there really is no supervoid that can explain the cold spot, simulations of the standard model of the universe give odds of something like 50 to 1 that the cold spot could simply have arisen through chance. Shank says that means scientists can't entirely rule out that the cold spot's being caused by an unlikely fluctuation explained by the standard model. The thing is, if that's not the answer, then there are some more exotic explanations. Shank says the most exciting of these is that the cold spot is being caused by a collision between our universe and another bubble universe. This all fits nicely into M theory, or superstring theory, which considers our universe to be just one of many in a multi-dimensional multiverse. If further, more detailed analysis of the cosmic microwave background radiation data proves this to be the case, then the cold spot may well become the first real evidence of the multiverse, containing countless other universes. This is SpaceTime. I'm Stuart Gary. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. There's new evidence that the Higgs boson decays into smaller elemental quark particles. Physicists with the Atlas experiment at CERN's Large Hadron Collider are reporting the decay of the Higgs boson into a pair of bottom quarks, one of 6 types or flavours of quark particles. The others being the top, up, down, charm and strange quarks. Previous researchers already found that the Higgs is capable of decaying into 3 types of gauge bosons: photons, W bosons and Z bosons. It's also been shown to decay into at least one type of fermion known as the tau lepton, which is a super heavy version of an electron. However, all these decay particles only account for about 30% of all Higgs decays. And the standard model indicates the Higgs should decay into bottom quarks about 58% of the time. Of course, that will still leave 12% unaccounted for. Bosons are force carrier particles, while fermions are particles of matter. Unlike the other bosons, which include the photon, the gluon, and the W and Z bosons, which are all known as gauge bosons and have integer spin, the Higgs is a scalar boson with 0 spin. First discovered in CERN in 2012, the Higgs boson has a mass of around 125 gigaelectron volts, and is produced by the Higgs field, which is thought responsible for electroweak symmetry breaking. I'm Stuart Gary. You're listening to SpaceTime. A Russian Soyuz rocket has blasted into orbit, carrying 3 new crew members bound for the International Space Station. The Soyuz FG rocket launched into the evening skies from the Baikonur Cosmodrome in the Central Asian Republic of Kazakhstan on what was a 6-hour 4-orbit fast rendezvous flight to the orbiting outpost.
15 seconds away from the liftoff. Again, not tracking any issues with the vehicle, everything pointing to go.
Vehicle to internal power.
Auto sequence initiated, vehicle now on internal power. The launch command has been issued. Rocket engines firing.
Second umbilical tower.
Power is going to start ramping up.
Engine turbopumps at flight speed. Engines at maximum.
Turbo pumps at flight speed and liftoff. Sergei Rosansky, Randy Bresnik, and Paolo Nespoli rocketing away from Baikonur and on their way to the International Space Station.
And liftoff.
The core stage's 4-chambered RD-108A engine and its 4 strap-on 4-chambered RD-107A boosters all ignited at liftoff, launching the 50-metre tall rocket into the darkening skies.
The very bright first stage engines cutting across the night sky there on Baikonur.
25. 20 seconds into flight. All systems are
getting reports, everything running nominally or normally for the first stage, so getting good first stage performance so far. Soyuz delivering about 930,000 pounds of thrust with those 4 boosters and the single core engine.
Is nominal.
They're going to be burning liquid fuel for the first 2 minutes and 6 seconds of the flight. Already past 1 minute since liftoff. Velocity already approaching 1,100 miles per hour for the Soyuz spacecraft.
You Roll pitch nominal. Copy. 70 seconds into launch. Everything's nominal on board.
And continuing to get good reports from the controllers in Baikonur. Everything looking good with the rocket so far as the first stage continues onwards.
Into flight. Everything's nominal on board. 90 seconds into flight. Stage 1 and 2 thrusters are working nominally. Roll pitch and yaw nominal.
And we have confirmation that the escape tower has been jettisoned and the 4 strap-on boosters flying away, making something known as the Koryov cross. The 4 strap-on boosters now detached. The first stage has done its job. Then the core stage of the second stage continuing to burn now. At this point, the rocket already 28 miles in altitude. The Soyuz traveling at over 3,300 miles per hour.
150 minutes in seconds and into flight. Second stage, thrusters are working nominally.
Everything continuing to look good with the second stage. Getting confirmation from the visiting vehicle officer that the launch shroud, so that protective shroud around the Soyuz spacecraft, has been jettisoned. So Soyuz now exposed during the additional climb to orbit.
All parameters are nominal.
At this point, a little over 3 minutes since launch, the Soyuz rocket traveling at a speed of over 4,700 miles per hour.
Into flight.
The strap-ons burnt out and were jettisoned after 117 seconds at an altitude of 45 kilometres, leaving the core stage to continue firing until 285 seconds after launch and an altitude approaching 169 kilometres. At which time the upper stage is then ignited while the core stage is still attached in what Russians call hot staging. 2 seconds later, the core stage is jettisoned, leaving the upper stage's RD-110 engine to fire for 4 minutes, bringing the Soyuz MS-05 into orbit 8 minutes and 45 seconds after launch.
Stability.
Everything continuing to look good with the Soyuz rocket. Being propelled by that single engine of the third stage provides about 67,000 pounds of thrust and is going to burn for 4 minutes and 2 seconds.
Guys, we read you loud.
The third stage performs an avoidance maneuver and then drops away. And getting confirmation from the visiting vehicle officer, all of the antennas and the solar arrays have been deployed, so that's always a good sign. The Soyuz now going to orbit at this altitude that's going to be raised over the next 6 hours by a series of different burns to place it in close proximity to the International Space Station. But a flawless launch, a flawless opening of all of those antennas and arrays. The crew now in orbit control of the spacecraft from here on out will be overseen from the Russian Mission Control Center just outside of Moscow, but a very happy Rosansky, Brezhnev, and Nespoli obviously in space and on their way towards the International Space Station.
Once in orbit, the Soyuz performed a series of 4 delta velocity burns to place it into its fast rendezvous trajectory to the International Space Station, docking with the Russian Razvet module 6 hours later.
Range is...
So the crew moving very quickly, actually ahead of schedule. Already in their final approach. Docking originally slated to happen at about 5 p.m. Central, but looks like they were able to move things very quickly, not having any issues with the vehicle. And so already in their final approach, under 150 meters away, heading towards the Rassvet module and a dock to the International Space Station.
64, copy. The crew is talking to each other. Range is 120 meters. Range rate is 0.71. External video cameras are working nominally. We copy. Guys, do you see the docking node?
The Soyuz well in view now, under 100 meters away.
And it's a little bit up by 90 meters.
The docking probe will be making contact with the Rassvet module. There's a docking cone, and that'll be able to make that initial contact and capture, and then a soft dock for a series of latches engaged, and then hard mate the Soyuz vehicle into place. Just about 75 meters away, continuing to close. It's at about 0.3 of a meter per second, and is going to continue to slow down during the very final phases of this approach, but everything lined up, everything going very well with the vehicle. Nighttime starting to come into view on the Earth below.
And external cameras are working nominally. We'll copy.
MS-05 just 67 meters away.
50 is the range. 0.2 is range rate. External cameras are working nominally. And we confirm that SSVP docking system readiness is illuminated. The line is illuminated. The hooks are open. SSVP is ready. Docking system is ready. Affirmative. Range is 40 meters. Range rate is 0.19. And external cameras are working nominally.
So continuing with the theme of the day, everything going great with the spacecraft and all of the systems on board the station during this final approach. Just about 40 meters away from the Rassvet module. The Soyuz MS-05 closing in.
Range is 35 meters. Range rate is 0.14.
Just under 10 meters away. Almost there. Standing by for capture.
The crosshairs are aligned.
2 метра. Есть касание, есть подвод, есть механсоединка, есть цепка.
Contact confirmed.
And contact and capture confirmed. The station and the Soyuz flying 252 statute miles over Germany. Soyuz MS-05 vehicle docked to the International Space Station.
We close.
So with that, the docking probe will retract, bringing the Soyuz closer into Rassvet, and then they'll be able to begin the final stages of docking, which will be the series of latches engaging both on the Soyuz and on Rassvet to hard mate or really hold the Soyuz vehicle in place. But again, docking confirmed 4:54 p.m. Central Time, 5:54 p.m. Eastern Time, while the station was flying 252 statute miles over Germany.
The Expedition 5253 crew will conduct some 250 scientific experiments while in orbit. These will include investigations into the pathology of Parkinson's disease, microgravity lung tissue studies into stem cell research, and the assembly and release of a microsatellite for low Earth orbit imagery for time-sensitive situations such as tracking severe weather events or monitoring natural disasters. The launch represented the 60th flight of the Soyuz FG rocket and the 5th for the new MS series Soyuz capsule. You're listening to Space Time. I'm Stuart Gary. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more Space Time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts or Audio Boom. This has been another quality podcast production from Bytes.com.